arrow or my resultant arrow, the tail end of it is my theta. There it is right there. My theta I'm looking for, and the magnitude I'm looking for that leg. So I've got to give me two answers on here. Step number one, what do? We're going to get my right angle, draw an arrow, and say this is hypotenuse. I know where my theta is now, and I know where my right angle is. This is my adjacent leg. The last one left over is my opposite. I'm going to grab my highlighter, and I'm going to say, what do I know? Okay? What is given to me, and what am I looking for? Well, this leg is given to me, and this leg is given to me. I'm looking for, yes, my other leg, and I'm looking for, yes, my theta. Let's get the theta out of the way, okay? So in this case, I have the A and the O. That's what I do know at this time. If we don't remember, then let's go ahead and write it in. So, ka, toa. What do I have? The A and O. Who is A and O? The tan. So, the tan of the theta equals O over A. Do I have the theta? No, I don't. The tan of the theta equals O, which is 1.4 over A, which is 1.2. Divide those numbers. Give me something. I need something from you. Okay? We're going to come back and answer that later. Part 2. I'm looking for the hypotenuse. If I have the other two legs, I can Pythagorean a squared plus b squared equals c squared. Or 1.2 squared plus 1.4 squared equals c squared. Don't forget, you need to square root this after you get done to find the c equals blank meters. Okay? Exhausting? Yeah, I know. I know you can do it though also. We've got practice problems to continue to practice. You have to practice. You're not going to get better unless you practice. So please practice some more. Okay? We will come back if you're having problems, if you want me to. Okay? This Friday, I'm not going to have time in class, but next week, when we have our classes, we can absolutely go over them, or I can send you the picture of them if that's what you want. I can do that too, but you need to start practicing on your own. Let's turn the page. Ooh, now we're getting to some other stuff, some more good stuff. This is nothing but good stuff and good stuff. Now let's talk about projectile motion. When you watch the Mythbusters, they use the word projectile. When that bullet was shot out of the gun, that was a projectile motion. Projectile motion is a motion of an object moving in two dimensions. I can put on here the X and the Y. That's what we're talking about. We're talking about doing kinematics in the X and the Y axis at the same time. Okay, let's keep going. Objects that are thrown or launched into the air and are subject to gravity. Remember we talked about that free fall? Are called projectiles. Example, you want to throw a softball. Or if you hit a softball with a baseball bat. An arrow. darts, bullets, a jumper, somebody who's just gonna, they're just gonna go for it. They're just jump. A circus clown shot out of a cannon. Like, there's so many examples, okay, of projectiles. Okay, again, one more time. If it's thrown or launched somehow into the air and gravity is the only thing acting on it, okay, and it's going to be in free fall, then we call it a projectile. Okay, now projectiles, they follow this path, okay, the trajectory. The trajectory of the path is called a parabola. Oh man, more geometry. Okay, so this path is the parabola shape that projectiles take. So let's go ahead and look at it over here. The coyote. You've seen this on cartoons. And what do they do on the cartoons? He runs off the cliff, and what happens? He goes straight down. Is that legit in real life? No, it's not. Could he run off the cliff and go this way forever? No. Can he run off the cliff and he's going to go in this direction? No. None of those are real situations. That's not going to happen. That's not going to happen. That's not going to happen. What is he going to do when he falls off the cliff? He's going to form a parabola shape. It may not be this big, but it's still going to be a parabola shape. Okay? Let's keep going. Without air resistance, right? When we're talking about a vacuum, a projectile headed into the air would be traveling this parabolic path. But on Earth, though, we have these air molecules, right? And if we were to throw a football, it's going to collide with the air molecules in the air while it's traveling. Now, because of that, it does cause it to take a shorter path, which is not exactly that parabolic shape. So when this girl hits the soccer ball, it should go this direction up here. But because of air molecules, we know that it's going to land in front of it and is going to take a shorter path. Why doesn't it take the true parabolic shape? Well, because of air molecules. Okay. Is it such a big, significant difference? No, not really. It's really, really, really minute difference. Does it matter in some things? It does. I mean, it matters about airplanes. It matters about having rocket spaceships go into outer space. It matters about figuring out the parabolic path that the satellite's going to take as it travels around in the Earth. Okay? So yeah, it does matter, but it's not that much of a big difference. Okay? So, because it's not that much of a big difference, in this class, we are going to ignore air resistance. And we're going to assume that all projectiles here in this class are going to take the beautiful parabolic path that it's supposed to take. Projectile motion is like a free fall. Question. Why? Because the initial velocity of any free fall object is going to be 0. And we're going to talk about that, okay, in a little bit more. It says here, though, we will always, one more time, just in case if somebody's asking, neglect air resistance. And therefore, the horizontal velocity, what's horizontal on the graph? The x-axis. On the x-axis is going to remain constant. And we're going to go into more details on how this works and why it works like this. So, we have an equation here that we use. It's an equation that we've already used. This is going to be in the x-axis direction equation. So when we're talking about an object that's a projectile, we're still going to use our kinematics, and it's going to be in the x direction, which is side to side. Okay? my equation that you normally are going to see is d sub x equals v sub x times t. And actually, you've already used this equation. You've used it so much, you probably have it memorized. Here's this equation written in a different way. V equals d over t. It's just put into the triangle, rearranged algebraically, and now it says d equals v times t. So these two are being multiplied with each other. D is the horizontal distance. V sub x is the horizontal velocity. T is the time. It's in seconds. Okay. Let's keep going. So it says here, as an object falls, regardless of its dropped straight down or launched into the air like a projectile, well, it will fall to the ground at the same rate. And we talked about that in class. I mentioned, I don't care if you have an elephant and a penny. If they were launched from the same height of a building, they're both going to fall or have the same acceleration rate on them. What is the only thing touching the penny and the elephant as they fall? Gravity. Nothing else is touching them. Why? Because we're going to ignore air resistance. Is somebody pulling up on them? No. Do they have a parachute? No. So they're going to fall at the same rate. Says here, though, examine the diagram over here of these two balls. There's a red one and a yellow one. Now, the red one was actually released and dropped straight downward. And the yellow one took a parabolic shape, okay, because it's a parabola. What's happening here? This curved out, this fell straight down. This was the Mythbusters that you watch. They had a bullet and it just fell to the ground, and then they had a gun that shot the bullet and it went straight outward. And when it went outward, it curved and came down. It eventually landed. And what happened to that bullet? Whether it was dropped or whether it was shot from the gun, they both fell at the same time. Why did they fall at the same time and hit the ground at the same time? Because both of them, once they were launched into the air, what was touching them? Nothing but gravity. And gravity doesn't discriminate. It doesn't care whether you're big as an elephant or if you're small as a bullet. It's going to pull on you negative 9.81 meters per second square, no matter what size you are, shape you are, or anything else. Okay? We're going to get into, we'll continue to talk about this a little bit more later. So, as we examine, we look at this, they're going to fall. Look at this one. By the time, and this is seconds, and they're like so quick. This is pictures taken, and it's just so fast, just taken so quick, so many pictures in such a quick time. Let's just pretend that this is a 0.5 seconds, and this is 1 second later. Look, by the time 1 second happens, if we were able to have like a camera that can shoot so many pictures so quickly, I can see that both the balls are at the same location in 1 second, even though one was launched out and one was dropped straight down. Okay? And you saw that in the picture on the Mythbusters. Since velocity is this constant in the x direction, hint, hint, guarantee you test question, but you're going to have to know that. We'll talk about that more. And acceleration is constant in the y direction. We use two different equations combined for this. When we talk about the x direction, right, we're talking about side to side. When we talk about the y direction, we're talking about up and down. Okay? The x direction equation, you saw it on the other page. D sub x equals v sub x times t. Okay? Over here, when it's the y direction, the equation that we use, which is the same kinematic equation, is d sub y equals vi times t plus 1/2 a t squared. And this v sub I is really a v sub I sub y. Okay, I know there's so many letters. This is the same equation. Remember when I told you when in doubt, this is probably the equation you're going to use? Well, look at this here. When we're doing a free fall equation that's falling in the midst of the air by itself, then this is the equation. This is the only equation you're going to use in the y direction. This is the only equation from the kinematics that you're going to use in the x direction. I'm telling you. How do you know whether it's the x or the y direction? You're going to do a drawing, and these drawings are going to be very helpful. You're going to have to start drawing. Don't be embarrassed of your drawing skills, okay? Mines are bad too. Let's practice this. Again, we are going to go through this and practice some more together on Friday and next week as well. The Royal George Bridge of Colorado races up 321 meters above the Arkansas River. Now, suppose you kick a little rock horizontally off the bridge. The rock hits the water in such a magnitude of its horizontal displacement to be 45 meters away from the bridge. Find the speed at which the rock was kicked. Okay? How do I know, Miss Munson? Is this object, which is the rock, in free fall? Yes, it is. It's in the midst of the air. So I'm going to use the x and y components, and that's what we call them. We don't really call them x and y direction. We call them components. The x and y components to solve for this. But to help you visualize it, I'm going to do a T-chart and a drawing because it's going to be helpful. Again, I show you the steps that I use personally to solve it. You can use your steps, but you better show me your steps. Okay? So let's go ahead and look at this. First thing is, I'm going to go ahead and I'm going to draw the bridge. And there's a person up here, and they got this rock. And they're going to kick the rock out. Once the rock leaves the ledge, it's going to form a trajectory of a parabola shape. One more time. Once the rock leaves the edge of this bridge, the trajectory of this rock is going to be a parabolic shape or a parabola. It's going to look like this. Now, they told us a little bit of information. They told us that this bridge is 321 meters above the ground. Vector or arrows are going to help you. 321 meters. They also told you that the magnitude, which is the number of the horizontal displacement, is 45 meters. Horizontal, what direction is horizontal? Side to side. Right? Not vertical. Vertical's up and down. We're going to use the word horizontal and vertical all the time now. So from here to here, this distance is 45. Okay? What else? They would like to know, find the speed, question mark velocity, at which this rock was kicked off of the ledge. So this rock was kicked in this direction, correct? But the moment it left the ledge, it started to make the trajectory of the parabolic shape. But it was kicked in that direction. So, question mark, what is the velocity here? Okay? Well, let's go ahead and do the next step. This is after I do my drawing for a free fall equation. I do a T-chart, an X and a Y T-chart. And I write my variables. So here are my variables for the X component or the X direction. D sub X, V sub X, and T. What are my components for the Y direction? or my variables. Here they are. It's going to be d sub y, VIY, A, T, and D. Those same 5 variables that we've been using on kinematics, let's write them down. They're going to be helpful. Okay? Now, let's fill in what we know. Again, arrows and drawings are going to be helpful. Do you see that this is horizontal? This would be on the x-axis. This is part of the x component. What is this number down here? It's a distance number. So the d sub x over here is 45. What am I looking for? Look at this arrow that I drew. I'm looking for, isn't that horizontal? So that has to be part of the x component. I'm looking for this velocity over here, the v sub x. The d sub y, the distance in the vertical up and down direction, 321 meters. Let's keep going. The v sub I, in this direction, how fast was it moving? What did our notes say on the previous page earlier? It said that all objects that are in free fall, its initial velocity in the y component or y direction is 0. Because look, before it fell and left the ledge, what is the velocity of it falling down? 0. What is the A? What is the acceleration of this? This is what gravity is pulling on it, because gravity is the only thing touching it. Negative 9.81. Don't forget the negative is just a direction. And they gave me the distance. Why did I do that again? The v sub f. There we go. Did they give me the t? No, they did not. Did they give me the vf? No, they did not. Now, this t-chart helps me out because I never know if it's going to be a 2-step problem or what. So I always do a t-chart. Now, I can stop and I can see, what am I truly looking for? Am I looking for the x components or the y component? I'm looking for the x component side. This is really the side I need. I need the v sub x and I need the t. Well, I don't need the t. I'm looking for the t is not even given to me. Look, nothing. Okay. So, can I go ahead and just solve by using this equation to solve for the x component? No, I'm missing 2 variables. So that means that I'm going to have to come over here on this side, solve this side, figure out what the t is over here, plug it in over here, and then get my answer. So it is a 2-step problem. But again, the t-chart is going to help guide you to that. Okay, so let's go over here. Step number 1. I have to go ahead and solve on the y component side first so I can find the t and plug it in over here. This is my y component equation. D sub y equals VIY times t plus 1/2 AT squared. Do I need to put this part in? Because what's the initial velocity? 0. So I'm going to go ahead and ignore that part. D sub y, 321, equals 0.5 times, yes, it's a negative 9.81, but does that negative have any numerical value to me? No, it doesn't. So again, I'm going to toss it out. 9.81 times, do I have t? No, I do not. T squared. Let's go ahead and solve this. 321 equals 9.81 times 0.5 is 4.91 times t squared. Divide by 4.91, cancel. Divide by 4.91. T squared equals 65.38. I'm not done. I have to square root it. So t equals 8.1 seconds. So I'm going to come over here and I'm going to go ahead and put 8.1 and 8.1. Alrighty. Now I can go ahead, do the second step, which is d sub x equals v sub x times t. D sub x, do I know it? Yes, 45 equals v sub x. I don't know it, but I know t is 8.1. Divide by 8.1, cancel, divide by 8.1. V sub x equals 5.56 meters per second. Not too bad. We're going to practice this so much. I promise you, you're going to get really good. Let's practice again. A rescue pilot drops a survival kit for her while her plane is flying at an altitude of 2,000 meters with a forward velocity of 100 meters per second. If air friction is disregarded, how far in advance does the survival explorer's drop zone should be when she releases it? Okay, so here's what we're saying. What do you do? Step one, you're going to draw it. So here's my airplane. There it is. Let's go ahead and let's draw the components that go along with this. Well, they told me that my airplane is above the ground. How far above? An altitude of 2,000 meters. And they told me that it has it's flying with a forward velocity of 100 meters per second. Okay? Now, I know that when they release it, it's going to be in the air. Anything launched, tossed, dropped in the air is going to form a parabolic shape. The trajectory is going to be like this. So this is where the package is going to land when they drop it. The last thing we need is these poor survivors are over here waiting for this package of probably food because they're starving. Do I want a person standing right here? No, that's the drop zone. That's the drop spot. Move out of the way. Well, I need to know, and they do this all the time in the military. They do this right now with the forest fires, right? Those people who are the pilots, they're driving these airplanes, and they have all the water and stuff inside their airplane. They need to do the math. They better have took some really awesome physics teacher class, so that way they can do the math to calculate how far in front of the fire do they need to release the water, so that way the trajectory can form the parabolic shape right here, land there right on the fire, and put the fire out before it burns anything else. Okay, so yeah, this is done in real life situations. I will tell you, last school year, exactly at this time last year when we were doing this in our notes, there was a military base here in the U.S. that was doing some practices. I don't know if it was North or South Carolina, but it was over there in that area. They had a whole bunch of people and they were practicing jumping. And so these military people were jumping out of the airplane. Whoever was their instructor obviously sucked and did not take an amazing physics teacher, because when they told those kids to drop, most of them or all of them ended up falling in a field of trees, breaking legs and limbs and stuff and hurting themselves. Why? Because their drop zone, which was wherever it was at, they dropped them and released them at the wrong time. So when they formed the parabolic shape, they ended up landing on trees instead of landing on the nice grass over here surface. Okay, so I bet they go back and they do their X and Y components and recheck their math. But that's just what I think. So let's go ahead. Now we have this. What am I looking for? I'm looking for the drop zone. It says here that it should be released. So I'm looking for from here to here, question mark, that distance. Okay, well, let's go ahead and do the next step that I told you earlier. I'm going to go ahead and I'm going to do my X and my Y t-chart. Okay, D sub X equals V sub X equals T equals, again, dy, VIY, A, T, VF. Okay, now let's go ahead. This is what I'm looking for. Do you see my arrow is a horizontal arrow? So that is my X distance. Question mark that. Do I know the X velocity? Yes, 100. Do I know the time? No, I do not. Do I know the distance on the Y? I do, 200. Do I know the initial velocity? Before the package was released, it was 0. Do I know acceleration? The moment it becomes released in the air, negative 9.81. Remember, the negative is just the direction, so I'm going to ignore it. T was not given to me. Do I know my final velocity? Bam, when it hits the ground? I do not know that. So that is going to be an X. Now, what side am I looking for? Am I looking on the X component or the Y component? I'm looking on the X component. So where goes my highlighter? Here it is. I'm going to go ahead and highlight this side because that's the side I'm looking for. I mean, you can easily get lost and confused if you don't label and highlight. That's why there's a highlighter in your bag. So let's go ahead and ask ourselves, can I use the X component equation to solve? No, I cannot. Why? Because I'm missing 2 variables. So that means that this is a 2-step problem. I have to go to the Y component side, solve for something over here to plug in over here. What can I solve over here to plug in? The T. The T is a variable that is going to be the same on both sides. If I know the T on one side, I know the T on the other side. Why is that? Time is a variable. It doesn't matter at what location you're at. T is T. Okay? T is not going to be, okay, when it's released, let me get a stopwatch for the Y component and let me get a stopwatch for the X component. Ready, set, go. They start both stopwatches. What happens if they start at both stopwatches at the same time? They're going to calculate the same time. You know, 0.1 seconds, 0.2 seconds, 0.3 seconds, 0.4. They're going to go at the same exact time, if that makes sense. And so because of that, you only need 1 T, and it's going to be the same on both. Okay? So let's go ahead and do step 1. Step 1 for us is the Y component equation, which is D sub Y equals VIY times T plus 1/2 AT squared. Don't forget the VI and the Y